Now, I want to revisit synthetic traps for just a moment. We saw synthetic traps initially in chapter 11. And just as a review, we see synthetic traps when a specific transform in a retrosynthesis would lead to an undesired reaction in the forward direction. In general, synthetic traps arise when a functional group we want to leave alone is reactive or labile. So, right, the word for this is labile, right, under the reaction conditions. And that just means that that functional group is reactive. So that's just another synonym for that. Now, we can overcome many of these difficulties presented by synthetic traps in one of two ways. We can either use a selective reagent, which is really what we focused on in like the previous section, right? But another way to do this is by using protecting groups. Now, when I did synthesis, I synthesized peptides and we used protecting groups all the time. So protecting groups is really a very versatile way to help with these kind of side reactions that you don't want to have happen. So let's talk about and review some selective reagents. Just as a reminder, when two or more outcomes are possible for a given reaction, the actual result often depends on the specific reagents that are used and the specific reaction conditions. In these situations, a reaction can be chosen to facilitate one outcome over another, and that's a selective reaction. So that's just a reaction that can be chosen to facilitate one outcome over another. Okay, and a reagent that's responsible for this is called a selective reagent. Okay, so we actually first saw a selective reagents in chapter 9 in the context of a competition between nucleophilic substitution and elimination reactions. So even though SN2 and E2 reactions tend to compete with each other, given that strong nucleophiles are often strong bases, we can choose specific reagents to selectively favor one reaction over another. So you're already familiar with this. So an example of that is that if we use Cl-, which comes from NaCl, it's going to favor an SN2 reaction, right? So this favors an SN2 reaction, whereas if we use the tert butoxide anion that we see here, then that would favor an E2 reaction. So we already have learned to use these selective reagents. We also saw another example so this example is from chapter 9, okay? We also saw another example in chapter 11, where we looked at the alkylation at alpha carbons of ketones and aldehydes. Remember, right, that lithium diisopropylamide, which is LDA, is a base. So this is a base that irreversibly deprotonates. Ketones and aldehydes. Okay, and it's selective for alkylation at the less substituted alpha carbon. Now, when we look at CH3COK, right, that's selective for alkylation at the more substituted alpha carbon. And so it, remember, deprotonates these reversibly. right? And this, it's just been a minute since we've done chapter 9 and chapter 11, so I wanted to review that. Now, another example of this is nucleophilic addition to alpha beta unsaturated compounds. So nucleophilic addition to alpha beta unsaturated carbonyl compounds, remember that occurs with very strong nucleophiles like Grignard reagents, right? And these are going to add selectively for direct addition. And I want to remind you, a synonym for direct addition is 1,2 addition. Okay, and that's going to add there. And then weaker nucleophiles like the lithium dialkyl cuprates selectively add to the beta carbon in conjugate addition or 1,4 addition, right? And we reviewed this. This is all originally from chapter 18. So we have seen these quite a bit. So let's do it again, okay? How would we carry out the synthesis shown here using any reagents necessary? When we look at this, we first off have to have a really good grasp and remember all of the reactions we've talked about so far, okay? But here are some questions you need to ask yourself. When a carbon-carbon bond forms to the carbonyl carbon of an alpha-beta unsaturated ketone, what functional group is produced? Okay, so the first thing you need to recognize here is you are starting, right, with an alpha, put my alpha over farther than I wanted, with an alpha beta unsaturated ketone, okay? And I just want to remind you that alpha and the beta are counted from this carbonyl carbon. So alpha, beta, and unsaturated refers to the double bond right here, okay? And so when we think about this, to form the carbon-carbon bond of a carbonyl carbon, an R nucleophile, so an R minus nucleophile, can add to the C double bond O, right? And that will convert to a COH right after the acid workup. Now, notice though, here's our problem. The target here, right here, is not an OH, right? It's a ether. Okay, so the target here is an ether group. So we can begin the retrosynthetic analysis by undoing a Williamson ether synthesis, right? So the fact that that's an ether, that's a clue that the Williamson ether synthesis is what we need to do. So when we think about this, and you all couldn't see that, but I waved a lot of arms there, and now everybody's looking at me in my house like I'm crazy. So just enjoy that visual there. Don't worry. When I teach this, when we review this in class, I promise I'll wave my arms a lot there too. So we need to undo a Williamson synthesis here, right? And so when we undo it, that's where we see that alcohol. And then we undo a Grignard here. To add the carbon-carbon bond, okay? So when we look at this, right? And so I didn't say much about how we're going to add the carbon-carbon bond, but I find that a Grignard a lot of times is my go-to, okay? And the reason that Grignard there is a go-to is because it'll selectively add by direct addition, right? So when the second question here, which is what type of R nucleophile will selectively add by direct addition, it's that Grignard. Okay. And so now we need to write this in the forward direction, thinking about all of our reagents. So when we write this in the forward direction, right? And then we're going to use an ether. And H2O. That gives us that product. And then for this, we can use a sodium hydride, right? CH3I. And there we are. So we carried out the Williamson ether synthesis by treating the alcohol with the base. So the sodium hydride really here is acting like a base, right? Followed by the alkyl halide. Okay, and so that's how we could attach that CH3 group right here, right there. Okay, all right. So let's talk. So we talked a lot about selective reagents, and that makes it possible to exploit differences in the reactivity of functional groups when we want one group in a molecule to react, but leave another alone. There are times, though, where that's just unfeasible. Like when a step in a synthesis may require the use of a reagent that would react with two or more functional groups. And so in situations like that, we want to be able to use those protecting groups to temper. And that what those do is they temporarily make one or more functional group unreactive under the specific conditions the reaction calls for. Okay, so after you make the desired change in the molecule, we need to be able to remove the protecting group and restore the original functional group. So after making the desired change, we must be able to remove the protecting group and restore the original functional group. So in this chapter, we're going to focus primarily on protection of carbonyl groups in ketones and aldehydes and protection of hydroxyl groups in alcohols. So the use of protecting groups have become a mature subdiscipline of organic synthesis, and there are entire books on this topic, and there are entire classes in graduate school on this topic. So there are many different functional groups that can be protected in many different ways. You can buy reagents that already have protecting groups on them, like in the case of peptide synthesis. So there are a lot of factors that we look at and consider when choosing a particular protecting group. So I like how there's a schematic here that shows the use of a protecting group. So suppose we have a molecule with functional group A, okay, and we don't, and we want to convert it to another functional group B, but another label, and remember that's just a label group is reactive, that's what that means, would also be changed in the process. And so the direct conversion of group A to group B is impossible without this group reacting as well, okay? And so we can work around it by incorporating a protection step, and all this protection step does is selectively change the label group to another functional group that's not reactive, okay, in this reaction. And so what that means is, and the term we use is the label group is protected when it's in that unreactive form. And then after that desired reaction is carried out, where we take A and we change it into B, then the original label group is restored in a deprotection step. And so I want to point out here that reversibility is important when you add a protecting group. So a good protecting group, right? A good protecting group is unreactive in one set of conditions, but is removable under a set of mild conditions to restore the original functional group at the same location. Okay. So this is how protecting groups work. Let's look at some examples where we would need a protecting group, okay? Look at this reaction. It'd be a poor choice to protect a carbonyl group of a ketone by converting it to a methylene group, okay? Using a Clemson reduction. So this, remember, is a Clemson. Because we don't know any reactions that would allow us to convert CH2 back into the carbonyl group selectively. So there's no real way to do a deprotection step here. So this would not be a good protecting group, right? But if we look at this, okay, ketones and aldehydes are most often protected by converting them to acetals. So ketones and aldehydes are most often protected by converting them to acetals, okay? And that's shown here in this equation. Now, an acetal, I want you to remember, has the form RO, where we have a carbon and then another OR. So we've got these carbon-oxygen bonds. So that carbon's involved in two COC groups, and this resembles an ether, okay? Acetals, like ether, are going to be really resistant to strong bases and strong nucleophiles. And if you want to revisit this subject, you need to go back and review chapter 9, right? They're also resistant to oxidizing and reducing agents. Now, an acetyl can be formed by reacting a ketone or aldehyde with excess alcohol under acidic conditions. We talked about this briefly in section 19.4, okay? Fortunately, the carbonyl group of a ketone or aldehyde can be recovered by hydrolysis under mildly acidic conditions, right? So this is hydrolysis under those mildly acidic conditions, and we can recover and get that functional group back. So a commonly used alcohol in protecting ketones and aldehyde is ethane 1,2-diol, which is also known as ethylene glycol, okay? Ethylene glycol is a popular protecting group in part because it has two hydroxyl groups on the same molecule. So only 1 molar equivalent is needed to protect a carbonyl group rather than 2 molar equivalents that would be required if a mono alcohol were used. And a mono alcohol, mono means 1, there's just 1 alcohol group. And so it reduces the amount of reagent we need. Another thing here is that the acetal it produces consists of a 5-membered ring, which is relatively stable, and so it favors the formation of that acetal. So very, very common ethylene glycol. So let's look at a retrosynthetic problem. So to see how a protecting group might be used, I want us to propose a way to carry out the synthesis of equation 21.24 here. When we look at this, we are going to need a carbon forming reaction, right? A carbon-carbon bond forming reaction. Notice also the product has an OH group, characteristic of an alcohol. So it may first appear that we can arrive back at the starting material through a transform that undergoes a Grignard reaction, like what we're seeing right here. However, right, we now have a carbonyl group, which, if you remember from chapter 18.5, is incompatible with Grignard reagents. Okay, so now we have a problem. So the workaround to this, we can, instead of using we can envision using a Grignard reagent where that carbonyl group is protected. So look at this, right? We protect that carbonyl group with the ethylene glycol right here. Then it can undergo the desired Grignard reaction, and then we can undergo a deprotection step and remove it. Okay, and so that's how we can build this molecule. Now, so then of course the question is, well, how do we synthesize the protected Grignard reagent? We know from section 26 that the Grignard reaction is produced from an analogous alkyl halide. And to avoid the presence of the carbonyl group on the Grignard reagent, the carbonyl group should be protected prior to the addition of magnesium. Okay, so the retrosynthetic analysis would look something like this, where you would undo the Grignard formation, the protecting group would already be there, and so then you would undo the protecting group formation, that acetyl formation. So in the forward direction, we would put the protection group on first, then make the Grignard reagent, okay? Because you can't make the Grignard reagent first because making the Grignard reagent is incompatible. So we have to protect it first and then make the Grignard reagent. So alcohols are really weakly acidic, and they can react with nucleophiles, so they are prone to elimination under acidic conditions, and we saw that in chapter 20. They're also prone to oxidation too. So depending on the specific synthesis, we need to have a lot of protecting groups. And so table 21 here shows different ways that we can protect the OH group of an alcohol in the form of either an ether or acetal, because ether and acetals tend to be very unreactive. For entries 1 and 2 here, right? The protection steps produces an acetyl, but this occurs through really different reactions. And so you can see the comments here talking about the reactions there. The protection step on entry 1 is a Williamson ether synthesis, and in entry 2, it's an acid catalyzed addition. If we look down here at entry 3, the protection step involves an SN2 to produce a silyl ether. And this is very common in protecting groups, is some sort of silicon there. And so this is something that shows up pretty frequently in protecting group chemistry. Now, you also will notice on this table, here is the deprotecting step with some comments as well. So a few things kind of to be aware of here is that even though there are multiple options that are available to protect an alcohol, they're not always interchangeable. And so you have to consider whether the conditions required for the protection and deprotection will interfere with functional groups elsewhere. So, like, for example, right, entry 1 here calls for some basic conditions in the protection step and acidic conditions in the deprotection step. So that would be a poor choice if other groups in the molecule react either under basic or acidic conditions. Okay. Entry 2 would be a poor choice if you need to avoid acidic conditions, because we've got acidic conditions both places. And then entry 3 should be avoided if the molecules have other sites that are nucleophilic or will react with fluorine. And the reason for this is in the deprotection step here, this is a nucleophilic substitution reaction where fluorine attacks the silicon. Okay, so just some things to kind of avoid there. Now, just as the carbonyl group of a ketone or aldehyde can react with a diol to produce a cyclic acetal, the same reaction can protect diols as well. So, for example, if you have a diol here, you can use the same reaction with a carbonyl group and get a protected 1,3-diol, and it's got acidic steps in both places. This is you can have a 1,2-diol, and you can also have a 1,3-diol. And so both of these are shown here as well. I want us to do, kind of this last slide, I want us to do a problem. So a student attempted to carry out the following reaction on this 3-hydroxypropanol, but it didn't work. And so suggest why and propose a synthesis route that would circumvent this problem. So when you have a question like this, the first thing you need to really think about here is what type of reaction did the student intend on carrying out? And so from this, we see a Grignard reagent. So it looks like the student wanted to do a Grignard reaction where the Grignard reaction acts as the nucleophile to add to the carbonyl group. Okay. And so then the question becomes, what undesired reaction would take place and what functional group would that involve? Well, this would not work because Grignards are strong nucleophiles and strong bases. And so the Grignard can deprotonate the weakly acidic OH group on the hydroxy alcohol, right? So we would end up having a side reaction so it can react with the OH as well. So that's a problem. And so what we need to think about is how can we protect the OH group? And one of the ways that we can protect the OH group is using dihydropyran, which is DHP. And so, for example, there's that. Now, DHP looks like this. So this is DHP, and that reacts with under acidic conditions. So we're going to use H2SO4, and that comes in and it protects the alcohol. Right, like that. And so this is that alcohol, and actually let me just highlight that for you. That alcohol there is that one there, because there's a lot of oxygen, so I don't want you to lose that. Then now this can go through the Grignard reaction. With an ether, and then H2O and H2SO4. And so now we have that molecule. And so this, by the way, here is the acid workup, which also functions as the deprotection step. So again, a lot of this chapter particularly really relies on the fact that, and they really make the assumption that you learned all the reactions leading up to this. So your success in this chapter is dependent on your ability to remember those reactions. And I know that you have a lot going on, so I really encourage you to go back and look at those reactions and refresh your memory if there are any that you do not remember, particularly as you're working through some of these problems. I also want to encourage you not to be frustrated. Remember, there are a lot of reactions that syntheses that can have two or more ways of going through the synthesis. And so it's just something that we have to think through. And this is something that organic synthesis groups do in research all the time, is they think through different ways to make really complicated molecules, and they try to predict which side groups would react, and they try to use protecting groups. So it takes a lot of practice. My suggestion is to work the practice problems, and of course, come see me if you have any questions.